suspension. A suspension is water with bigger stuff in it, pieces of cells or cells themselves. Does the interstitial compartment have a cell in it right now? Yeah, it's right there. The interstitial fluid is bathing the cell. Take a grape, it's a cell, throw it in a glass of water. The water is the interstitial fluid. Your cells are bathed in fluid. That fluid is an interstitial fluid. So your interstitial compartment contains interstitial fluid that is a solution because it has little things like sodium in it, have medium-sized things like protein in it, and have big things in it like cells, for example. Your plasma, your blood, has cells in it, right? You guys have heard of red blood cells, have you not? White blood cells, those are cells. Platelets are pieces of cells. So your blood, your plasma is a suspension. That's the example I gave you in your notes, if you look at your notes. Your plasma has protein in it. Plasma proteins, as you'll learn next semester in a ton of detail. Your blood has sodium in it, potassium, and chloride, and hydrogen, and bicarb, and carbonate, and calcium, and magnesium, blah, 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 blah. So, again, regardless of which of these fluids we're talking about that are contained in all these compartments, they're all three. Okay? Are we good? So now I can use those words freely. I can say solution, I know you know what I mean. And colloid, and suspension, you know what I mean. All right? Very straightforward stuff. Now, what else does water do? Transport stuff. Okay, you guys have learned about the major systems of the body, right? You guys talked a little bit about the circulatory system. Circulatory system circulates stuff. How does it get circulated? Your blood. Your blood is a lot of water. About half of your blood is water, roughly. And it's taking stuff from point A to point B. That's how your cells live. Fluid electrolyte balance, something we'll talk about next semester. This all has to do with a molecule of water helping balance other things in the body, like electrolytes, for example. It'll help balance pH, it'll help balance a whole bunch of stuff. We already talked about what water does when it comes to cooling your body and sweat. Helps maintain homeostasis in general. Again, that's a common theme here. Regardless of what molecule we talk about, it's all about homeostasis when we talk about phys, because that's what physiology is. If somebody asked you, give me one word for physiology, immediately what should come to your mind is homeostasis, or vice versa. If somebody said homeostasis and you're supposed to spit back a word at them, it is, because that's just what it is. Okay? Good? This we're not going to spend a whole lot of time on, the second inorganic, and that's electrolytes. Although that's spelled incorrectly there, I'll assume it's spelled correctly in your notes. Ions, it's the same thing. Okay, we have these small charged particles here that when they're in water make up a solution, by the way. Now I have a number of abbreviations here. These are some of the basics: sodium, potassium, calcium, chloride, bicarb, carbonate, phosphate. I assume that you know what those are. So on the exam, I will have every once in a while abbreviations of molecules. It'll be nothing foreign to you. It'll be something that we specifically talked about in class, but you need to know what they are. And again, I'm just going to assume that you do it. If you don't, certainly I would learn it. Okay? When it comes to these ions, these charged molecules, these small charged molecules, they're in equilibrium. They make salts. So these charged ions come together to make salts. When we hear salt, we always think of sodium chloride, right? But this is a salt. Potassium chloride is a salt. Calcium phosphate is a salt. Calcium carbonate is a salt. It's just not table salt. We don't sprinkle those on our French fries. Right? These are other types of salts, but they exist within our body because we have these other molecules that exist, and we have this equilibrium, this chemical reaction that's occurring. That I'm going to assume, once again, you guys understand. All right? And we have to have normal values for these. There has to be a normal sodium level in your body, or things are going to go wrong. And when I say go wrong, what kind of things? Well, I'll tell you later, but worst case scenario is death. All right? Or at a minimum, you're having a crappy day. Yes, sir?
The positive charge are molecules are. Oh, wait a minute.
You good?
Yeah, it's already said.
Okay. All right. So these things do a number of things. They help us with communication. Action potentials, we're going to talk about that in a lot of detail in some weeks to come. All right. They're going to help us transport stuff across membranes. We're going to talk about that actually next week. And again, it's all about homeostasis. So I'm not spending a whole lot of time on this right now because we don't need to. And then the last thing here that we'll talk about, and maybe I'll give you a teeny bit of a break, although we're already a little bit behind. What time we get out of here?
6.
6? We got here at 6? Oh, you're not getting a break today. I'm sorry. I always give you a break in between lectures. I started a little bit late, plus we had some computer glitches, but I'll always give you a break sometime in between the class. I get about 35 or 40 minutes, I promise. Okay, today was an exception. All right, acids and bases. If we talk about acids and bases, we have to talk about pH. And a lot of times pH intimidates people. pH is very straightforward and easy. So just a really quick pH lesson here. So when it comes to pH, what is pH? It's the power of H. H is an ion, an H ion, charged positively. It's also called a proton. So those of you that take the chemistry classes, and everybody here has, okay, you'll hear the word proton, proton, proton. It's an H ion. It's the same exact thing. And so when it comes to pH, what is pH? Well, we're going to draw two separate containers. We're going to call it A and B. And in each of these is water. We're going to assume that it's the same volume of water. Those are all protons. Those are all H ions. Now, obviously, I drew more H ions in B than I did in A. So obviously, the concentration of H ions is higher in A or B. Obviously, it's B, right? So we have a higher H plus concentration in in B as compared to A. Okay? Now that's going to dictate what pH is, because that's what pH is. pH is a measured value. Okay, and there are numbers that are associated with pH. It's a unitless number, but it tells us what the concentration of pH is. And so when your H concentration is higher, your pH is lower or higher. We have to compare A and B. Which one has a higher pH, which one has a lower pH? We'll start with lower. The lower pH is in B, right? So this is going to have a lower pH. There's an inverse relationship between H plus concentration and pH. So this is obviously going to have a higher pH. So of these two, which one's more acidic? B's more acidic. The lower your pH, the more acid we have. And that's what H plus is in essence. That's what the acid is. So this one is more acidic. This one's less acidic or more basic, if that's what you want to call it. That's all pH is. So we have pH values of what? 5, 6, 7, 8, 7.3, 7.4, 7.5. And by the way, I want you to know what the normal value is in your blood, your arterial blood. It's in your nose. So if we were to draw our homeostatic level for pH in our arterial blood, there's our set point. Arterial, that's the blood in your arteries. Arteries are a specific type of blood vessel that take blood to your cells. We'll talk about it in a lot of detail next semester. So your arterial blood pH, a very important value that is measured routinely clinically. The set point is 7.40. Well, obviously we have a normal range, and our normal range is anywhere from 7.45 to 7.35, a very, very narrow range, but very important that it be maintained. Okay? To a chemist, that's peanuts. In the body, that's huge. You have a patient, and they have a pH value that's is 7, that's neutral, right? 7 is a neutral pH. 7, if your patient has a pH of 7, you're panicking. Your patient might very well die because their pH is 7 or 8. That's bad. Okay? So it has to be maintained within a very narrow range. And I'll tell you why later. Probably on Monday I'll tell you why. Okay, tonight I don't have time. But I do want you to know the normal range for pH in the arterial blood. All right? And we're going to talk a ton about pH next semester when we go into acid-base balance. We'll visit it a little bit this semester. Now, when it comes to the actual numbers, so I just said 7.35 to 7.45. Well, what on earth does that tell us about H plus concentration? How do we translate that? We do it simply with scientific notation here. So a pH of 7.4, for example, that's our set point value. How do we know what the H plus concentration is? Because that's what pH is measuring, right? pH is measuring the concentration of H plus. 10 to the negative 7.4. That's your concentration of H plus right there. If you have a pH of 7.4, I don't care. I don't care. That's what the value is. Do you have to know these specific numbers? Absolutely not. I'm not going to memorize this stuff. All right? But I'm going to assume that we know scientific notation. And I'm going to assume that we know how to read little teeny numbers like this. All right? And by the way, the practice exam is already on Pilot. And you'll see on that practice exam the kind of questions I'll ask that revolve around something like this, and every other thing that we're going to talk about for the first exam. Okay, so it's already on Pilot, and I encourage you to go to the exam and look at it now. I put the correct answers in a key at the end of the exam. You don't have to look at the key. Just look at the questions. All right? That'll kind of give you an idea of how to study. That'll kind of give you an idea of how to put the ideas, or how to put the material together, and how to integrate it, as I said in that email to you guys. Physiology, you need to integrate information. You need to be able to put it together. And if you can't do that, then you're going to be in trouble. All right? And if you don't know how to do that, that's when you get help from me, from the tutors, you know, the TAs, whomever. All right? So anyway, this is just showing us again how these numbers for pH equate into a concentration. Okay? Are we good so far?
Yeah.
Good. So those are the inorganics. Okay? Just scratch the surface, more to come later. Let's talk about organics now. We're going to start with ATP. ATP's main job in the body is provide energy. All right? And that's correct, but that's not the only thing ATP does in the body. Okay? Although I think the main thing we'll talk about for this course is its energy source. Now, I have a picture of ATP here. I have, you know, how it's defined. I'm not going to put that on the exam. It's not a chemistry class. I couldn't care less whether or not you know what the structure of ATP is. What I do want you to know, however, is adenosine triphosphate. There's 3 phosphates. So actually, really, this is what I want you to know. What we're going to concentrate on really with ATP, for right now, is how it's made. And so we have ATP, and if we're going to draw ATP simply, I don't know, let's just do this. 3 phosphates. It's that bond right there where we derive energy from ATP. Okay, so ATP is an energy source. You know, we all said that in unison. Well, what does that even mean? It's a molecule that gives the body energy. Well, it's specifically giving stuff within the cell energy in order for those things to work. And so there are enzymes in those cells that will break that bond. And when that bond is broken, it releases energy and it allows transporters, for example, to work. Things we'll talk about in detail in just a couple of weeks. So we lose that phosphate, but then it gives us energy. Energy is released when that phosphate is released. But then we have a molecule that the cell can no longer use for energy that just has 2 phosphates on it. And instead of adenosine triphosphate, we call this adenosine diphosphate. Di means 2. Well, that molecule is no good for us, or the cells, to make ATP. The other bonds between those phosphates, it doesn't give enough energy to the processes within the cells that will allow that process to work. So what the cells have to continuously do is that. The cells are continuously producing ATP by simply taking an ADP, which is present, and adding a phosphate, the P to it. That has a name. It's called cellular respiration. Cellular respiration is the process by which a cell makes ATP by simply sticking a phosphate on an adenosine phosphate. Okay, or diphosphate, yes sir? There is AMP, but it's not done for an energy source. It's done for other things. But yeah, is AMP something that exists in the body? Absolutely. All right, but it's used for other things. Okay, good question. All right, so this is what we're going to concentrate on now. How do we make ATP? There's two ways to do it. A cell can either use oxygen